All right, so good afternoon, everyone. How's everyone? I hope you had a decent break. So this afternoon, the topic we're going to be going over is a topic known as elliptic curve cryptography, which is one of the more exotic forms of cryptography. A bit hard, it can be a bit daunting for some people. It certainly terrified me for the longest amount of time. I can't say I'm an expert on the subject, but after going to the BSides Canberra conference and spending a few too many hours on one of the challenges, and I'll care to admit, I think I know a bit more than I did before. And so I'd like to say I'm at least somewhat qualified to give a workshop on the topic. But let's just hope I don't bugger this entire thing up. I hope I'm well prepared enough. Also, there's another quick, just some admin announcements. We still are looking to do some CTFs on like the weekends. So if anyone is, if anyone here would like to participate and hasn't, verified their role by DMing one of the admins their student IDs and would like to get access to the competitive challenges, just another reminder that that's a thing you can do. And particularly considering how well Melbourne Uni did during the BSides CTF, we're certainly looking to go up the rankings a fair bit and try and retake our spot of where we were last year, which was technically still behind Melbourne, but at least a bit higher up on the scoreboard. So, without further ado, I'm going to get started. So before I start, can I just get a show of hands? Who here has heard of elliptic curve cryptography, or who here is vaguely aware of it? Great, a few people. Who here thinks they know enough about it to, I don't know, maybe approach a CTF? Like, who thinks they could implement elliptic curve cryptography if they wanted to? Great. Who here has seen the number file video on elliptic curve cryptography? Yeah, I think that's the average kind of background. And I think a few weeks ago that's the background I had. It's I don't know. So anyway, without further ado, elliptic curve cryptography is a form of cryptography, funnily enough, surrounding the study of curves. Hello? Sorry, I'm cutting out a bit. Yeah, within number theory, an elliptic curve is just any kind of equation with the form. Now, correct me if I'm wrong. I think it's a y cubed plus b x squared y plus d y cubed plus e x squared. They get a bit complicated, plus f x y plus. I won't draw the entire thing out because the good thing we need to keep in mind is that within cryptography we only care about a very small subset of simplified curves. Now, there are three main types of curves within elliptic curve cryptography that are used. Those are known as Weierstrass curves, Montgomery curves, and twisted Edwards curves. And we're only going to be focusing on the very first of those curves. Now, a Weierstrass curve is just a curve in the form, it's very simple, y squared equals x cubed, what, did I miss the coefficient? Yeah, no, sorry, it's x plus equals x cubed plus ax plus b. And more often than not, these are, and in the context we'll be dealing with, these are usually integer numbers. Now, if you were to graph an elliptic curve over the real numbers, then generally it would appear to look something along the lines of this. This vaguely now, this is vaguely what's the elliptic curve that Bitcoin uses, which is the form y squared equals x cubed plus 7, which is one of the simpler ones to understand, probably because the only number other than the only integer in it is just the number 7. And so there are a few. Now, this might sound like a bit of a strange place to go in, but there exists a property of elliptic curves that mathematicians are particularly interested in, which is where if you have 2 points, or sometimes it's 1 point, but if you've got points on an elliptic curve, you can often do what mathematicians call an elliptic curve point addition, which is basically to add those points together. And the way that they've defined this is to say that if you've got a point here, say let's call this point A, and say we've got a point here, let's call this point B, to form the sum of A plus B, what we do is we draw a straight line between A and B, and wherever it lies. Now, it seems like a bit of a strange direction. What they do is they then reflect this down the axis and then say that this point equals C. Now, it might seem like a very strange and arbitrary decision to reflect it down, but hopefully it'll make sense why they do that in a short amount of time. Now, there's also a few other edge cases we need to take care of. The first major edge case that you might seem to run into is, what if you want to add a point on a curve to itself? Now, if you add a point on a curve to itself, so let's do a quick diagram here. Adding a point on a curve to itself is like saying, let's say you've got this point A. If you want to say A plus A, then you essentially draw a tangent line and find the point in which it intersects. And the other edge case we care about is the case in which one point is directly above the other. So for example, this point here, A, and this point here, B. In the case where A is equal to B, then the line goes up to infinity. And this specific edge case we give a specific name to. Some people call, it's often defined as the infinity point. However, for a reason that will make a bit more sense later, we just denote this with the number zero, with the symbol 0. And there's a few identities that we can have from working around with this. For any elliptic curve, there are a few identities that work for all additions anywhere on the curve. First thing to keep in mind is that for any point, if you got for any value of p, like any point p, adding that point p to 0 is going to be always equal to the point 0 plus p. So basically, it doesn't matter which way around you do it, which is always just going to be equal to the element p. And this should make sense, as if you've got, if you want to add, say, a point here p, and you want to draw a straight line upwards, it'll go to infinity intersecting this spot here, but then reflecting down it equals p. And fun fact, that is one of the main reasons why mathematicians decide to make these point addition associative, just so this kind of, calling this the identity, just works cleanly. And there's a few other things, such as the inverse law, which is where if you've got this point here, which is negative p, the addition of them two together is going to be equal to 0. So p plus negative p equals 0. And hopefully that should make kind of intuitive sense to you. And there's like associativity, which is a plus b plus c equals a plus b plus c, and then there's commutative. It's also commutative, so c plus b equals b plus c. And I promise that's all the maths I'm going to be using. Well, most of the maths I'm going to be using this afternoon. But the important thing you have to keep in mind is that for those of you that are mathematically inclined, it doesn't matter, you don't need to know this. The technical way to describe this is saying that addition along an elliptic curve forms an abelian group, which I just wanted to impress you by mentioning the fact that I know what the word abelian means. Hang on. So anyway. But now the thing we can keep in mind is that, one quick note is that, actually, I won't bother actually derivating the formulas for addition, but generally speaking, the way it works is that if you've got points on the curve and you want to say, add them together, the first thing you just do is you calculate the gradient, call that lambda, and depending on and there's different edge cases. In the case that, you're adding two different points, then it's just, y2 minus y1 over x2 minus x1, you'll probably remember that from year 10 maths. In the case where it's on a tangent to itself, you've got to do some implicit differentiation. So the curve is, y squared plus x cubed plus ax plus b. That just becomes 2y dy dx plus 3x squared plus. But basically, so that in that case, the lambda just equals that over this. And so the main thing to keep in mind is that there's no single formula for addition along an elliptic curve. But generally that you need to make several, so there are several edge cases you need to make, but generally speaking, it all intuitively works the same. You're just drawing a line on the curve and then adding where it is. Now you might think, how can I actually apply this to cryptography? How can I how can I make this work with numbers? Now, one thing you'll know in that in cryptography, all of these now as I mentioned at the very start, every single point on here, this is a smooth curve in the real numbers, meaning that all of the points here are represented by some ratio of integers. They're all rational numbers. However, as you all probably know, floating point arithmetic is very difficult, and cryptography with real numbers is an absolute nightmare. And so mathematicians generally prefer And so mathematicians generally prefer to, do this over what they call a finite field, or which just means to split this into a series of a series of discrete points. Now I'll give you a quick demo of what that actually means. Say we got this graph here. This is a Bitcoin curve I mentioned earlier. Y squared equals x cubed plus 7. But the step that mathematicians then immediately make is then they say it is mod 7. It is this, and then mod p. Now, if you've taken a discrete maths unit, you'll probably know what the modulus means, but that just means kind of restricting the number over it goes a certain value. It's like clock arithmetic, like 13 mod 12 is 1, or 6 mod 5 is 1, and just kind of keeps going over. To give you a quick demo of what this concretely means, remember what that graph looks like, and then I'll show you the exact version of it in here. Now, here is the exact same graph, however, with the restriction that every single point is only expressed if the point here, mod 17, is equal to y squared plus x. If the coordinates of each point are such that y squared plus x cubed equals 7 over a modulus of 17. And as such, it makes sense to kind of say that, we're not really caring about and so instead of this being a continuous curve over the real numbers, like most other graphs you're familiar with, an elliptic curve in this kind of sense is just it's just a finite field where each of the coordinates is just some coordinate where it solves that equation, and so it's just basically a set of all points in a square matrix such that these values kind of satisfy that equation. And so one thing you might want to have a look at immediately is how do you actually program with elliptic curves on a computer? How do you write algorithms that use them? Because very few people, I couldn't think of a fate worse than having to do elliptic curve multiplication on a pen and paper. And so you might want to think, how would I do this with a computer? So I'm going to have I'm just going to, oops. Oops, not going to open the flag for you. Oops, shit, I opened the flag, sorry. Pretend you didn't see that. Okay, let's make a new one. Now, usually when you're programming with elliptic curves, I would advise you install a program called Sage Maths. However, this program is but Sage Maths is about 3 gigabytes and takes a while to set up, so I can't really expect workshop members to actually have installed it firsthand. So the program I recommend you use is something known as TinyEC. And so what you can do is, you can say from tinyec.ec import. Now, I'm skipping over a lot of number theory here. Don't worry if there's a few numbers you don't recognize. I'll try and explain everything to the best of my ability. Now, let's say we want to add 2 points together. So, again, if we had, let's say we've got some point here, A, B, and we want to find the point here, C, such that, A plus B equals C. The way we would do this is we would define the points on the curve. First thing we would do is we would actually define the field in which the curve exists. So that is just to say, field equals subgroup B equals 17, because that is the value of P that we're assuming, because you saw here, oops, where was it? This is the curve that we are aiming to, make. X squared plus y cubed equals 7. So the actual the prime modulus is 7. So the prime modulus is 17. Now in this case we can say G equals 15, 13. Although actually no, we'll just call this 15, 13. Now this is known as a generator point. I'll get to explaining what that means a bit later. And then in this case I'll just say n equals 18. And h equals 1. Now in this case, this is known as these two numbers here, n and h, are the order and cofactor of the subgroup, but you don't really need to know what they mean. Now we can actually define the curve. So actually, I'll make this a bit bigger so people can actually follow along a bit better. Once you've got the curve defined, you can say, now in this case, the coefficient of x of x squared the coefficient of x is 0 because there's no x. It's just x squared, x cubed plus 7. So a equals 0, b equals 7. Field, and then now here we can say what we're going to do here is going to say g is equal to the curve.g. Now in this case, curve.g is what's known as the generator point of the curve, which is the point that we defined right here. Now in theory, I could define this to be any point on the curve, but in lots of cases, predefined curves come with a generator point that they recommend you use, and I'll try and get to that a bit later. But let's say we want to say, I don't know, now I'm going to try printing a combination of all these different curves. So let's say for I in range 130, print and then obviously there are coordinate points of each point. So g dot x and g dot y. And then we need to add g to itself. Or not to itself, to the actual original point here. So it's going to be going. Now keep in mind here that as you can see, it's going from 1513 to 210, and then notice here that it's going back 1513, and then it's immediately going back to 1513 here, and then this pattern repeats itself. What this means is that repeatedly adding along this generator point, it forms a cycle. And fun fact here, the number n, 18 here, this is the order of the group, which means the amount of times that you can kind of multiply before you get back to the original point, or basically the number of unique coefficients that you can use on scalar multiplication on any point along the curve. And to show you this kind of graphically, let's just say this is what it looks like doing this kind of on the curve. As you can see, the point that we started along here was this point G here, 13, 15, and then immediately jumped from 13, 15 here to 10, 2, as you can see from here, then to 8, 3. Yeah, and just, it goes on, and then the cycle repeats itself afterwards. And yeah. I won't bother explaining basically the cofactor thing I mentioned earlier is just the amount of subgroups there are, because in this case there's only one set of groups that it'll keep going to, but in some curves like like twisted Edwards curves, like ED, like I think some of the other systems use, they're all completely different. I won't get into that now though. But now you're probably wondering the actual bit that you came here for, the bit that's kind of left you scratching your head in the first place. Like, what the hell does any of this have to do with cryptography? How can you encrypt messages with it? How can you sign things with it? Like, how is this useful at all? I've just been drawing lines on a whiteboard for the last 20 minutes, or however long I've been doing this for. And the reason this is relevant to cryptography is due to one really, really important fact. Now, public key cryptography relies on something known as trapdoor functions, which are essentially something that is very easy to do in one direction, but next to impossible to do in the other direction. Let's say you've got some point, I don't know, I'll say point G, and then you multiply, you've got a point G, then you say n times G equals Q. If you give someone just the value of G and the value of Q, and you tell them, tell me what value of n went into this to find the value of q. Finding that value is very hard. However, multiplying this value is incredibly easy. And so as such, we can utilize this fact to make a crypto system that is easy to go in one direction, but hard to reverse. And so what we can do after that is, hang on. Because one thing that you might want to keep in mind is that in this case, actually, can I get another show of hands, like I did at the start? Who here knows anything about a Diffie-Hellman key exchange? Who knows anything about modular exponentiation or? Great. Well, you basically know the exact same thing. So the crucial thing to keep in mind is that the properties of an elliptic curve are practically the exact same as, so adding on an elliptic curve is, for all intents and purposes, can be treated equivalent as multiplying in a, integers mod sum p, because the discrete logarithm, because the Diffie-Hellman key exchanges and elliptic curve crypto systems rely on something known as the discrete logarithm problem, which is much more general than any specific operation, like whether it's multiplication or something. And so we can utilize this fact to make a strong crypto system. Now, and so let me show you a quick system of how you can utilize this fact to actually encrypt something. Now, I'm going to go back to the very classic example of two people trying to exchange messages. We've got one person here, Alice, and one person here called Bob. And let's say there's someone in the middle here that is a man in the middle, an adversary that can look at every single message that is being transferred between those two. Now, Alice and Bob want to be able to freely exchange messages. Their messages aren't being intercepted, they can't be read. However, their messages can't be intercepted. They're not being intercepted and modified. However, the messages being sent can be read by the person in the middle. I forgot what the convention for his name is in the middle. But here's what they do. The first thing Alice and Bob need to do is agree upon a curve to use, which is basically what equation to use, and they need to agree upon a generator point, which is just some arbitrary point on the curve, although some different curve specifications prefer different points for computational and security reasons. So the first thing they do is Alice and Bob agree on a value g. They both know g, and because it's public knowledge, this person here knows g as well, so that's not secret at all. Now, what Alice does is Alice generates her own private number here, so I call that NA. Now, Alice does not share this number with anyone at all. And then Bob generates his own private number, NB. And then Alice computes NA times G equals QA. And similarly, Bob calculates NB times G equals QB. And they send these two values to each other. And so now the adversary has QA and QB. And then what they can do is Alice then gets this value of QA and multiplies NA by it. So then they got NA times QB. And now keep in mind that QB is just, keep in mind that in this case, QA times, hang on. Yeah, so if they just combine these points together, they can come across what is known as a shared secret. So Alice then calculates NA equals QB, and our QB is just, that's just NA times NB times G. And Bob does the same. Bob calculates NB times QA equals NB times NA times G. And so Alice and Bob have arrived at the exact same number here, but in a way that the interceptor cannot figure out. And so it's basically two people agreeing on a key to use for encryption in a way that any kind of eavesdroppers cannot figure out. So what they usually do after that is they use a key derivation function on that point, on that value, to actually use a proper symmetric encryption standard such as AES. Now keep in mind that there are different schemes. You can use elliptic curves as a direct kind of public key crypto system, such as in the same way that El-Gamal can be used in Diffie-Hellman. There are El-Gamal versions of elliptic curves, but I won't get into that now. I'll leave that as an exercise to the viewer. But one thing you might actually question, one thing you might be questioning is, why is it so hard to figure out in one direction, to calculate in one direction, but not know in the other direction? And that is a very good question, and understanding that is kind of the reason why elliptic curves cryptography is so good. if you were to just simply add a number to each other, say ng equals g plus g plus g plus g n times, why can't an adversary just do the exact same thing but just keeping count to figure out what the value is? And if you're wondering why they can't do that in this situation, you'd be completely correct, because in this situation they could. But the reason this is so powerful is that there are better optimizations you can use for this. Can anyone think of an optimization they could use on how to, multiply a number by itself, other than just adding itself to itself multiple times? Anyone? Can you think of any specific? Sorry? Yeah. Can you think of any specific edge cases in which it would be very easy to do this? Okay, I'll start then. So think of one specific edge case where the n is a power of 2. So let's say, 2 to the 4 times g is just equal to 2 times 2 times 2 times 2 times g. Yep. And so in this case, even though you're multiplying by 16, you've done it in 4 steps. And so that is immediately a reduction of, that makes it a complexity of log 2. Rather than a complexity of n. That might not sound significant, but it really scales up. Now I won't go over it now, but in the case where it isn't a power of 2, this still works, because if you think about how expressing a number in binary works, every single number can be expressed in terms of sums of powers of 2. So what you can do is you can break the number in terms of powers of 2, and sum them all up and add them together. That's a bit more complexity, but generally it does make a difference. Think about it, and so think about it this way. Calculating, n to the n times g is equal to log 2 n steps. However, for solving the discrete logarithm, now, one thing to point out is that there technically are more efficient ways of solving this discrete logarithm problem. And so in practice, solving it takes approximately 0.86 times the square root of n, because correct me if I'm wrong, but I think that's the Pauling-Hellman algorithm, or that might be another one, I'm not sure. I'm just going to pretend it's the square root of n. So let's say you're doing this an actual large amount of times, which is something on the order of multiplying it by itself 2 to the power of 256 times. Now, as you can tell, this is now log 2 of 2 to the power of 256 is just 256 bits. It's just 256 bits. It's just the number 256. And so doing now 2 to the power of 256 is an astronomically large number. Like I can't even get around. I can't even remember how many digits it has. It's a lot. But the square root of 2 to the power of 256 is just equal to 2 to the power of 128. And 128 has about 78 digits in decimal and is approximately 340 billion. And so as you can tell, doing something just a few hundred times is a lot easier than doing it 340 billion times. So it kind of makes sense why this is a good kind of trapdoor function. And another thing to add, one thing I like this so much is because teaching someone why RSA is difficult takes a bit of knowledge about prime factorization and stuff. However, the word 340 billion just kind of resonates with people and it makes it a bit easier. So now we need to figure out how do we actually go about writing cryptography using this. And to do that, we're going to go back to our library, tinyEC. Now I'm just going to go, has anyone here had a look at the CTF challenges? Just another thing, I've put up a series of challenges relating to elliptic curves. People can have a look at if they want to. I'll be going through some of them. So the first challenge here is, I'll just go to the first one here, simple addition. In this case, they give you a custom curve. Now note here, the curve here is just like an educational curve. The number is only 9,000. In practice, it would be a far larger number. However, this is just a bit easier. And the first thing it's asking you to do is find the addition of these 2 points on the curve. So I'm just going to leave this as a comment here so I can remind myself. And this is pretty easy to do. So you just say, I don't know, f equals. Now in this case, the prime here, p, is equal to 9739. Also, I probably should have mentioned this at the very start, but please stop me if I say something that's confusing or you don't understand anything. This is a very obscure kind of obtuse topic, and I've got a feeling I might have lost a few people. So genuinely, please just yell out at me or raise a question or something. I don't know. Yeah, has anyone got any questions so far? Is there anything? Yeah, Marish? That is a very good question, and I skipped over this a little bit because I didn't want this to be a number theory lesson where I just derive formulas, but just for you, I'll do this. Oh yeah, sorry, good question. Yeah, so what Mariusz asked was if this is being done in a finite field, so let's say instead of being like a curve like this, in practice what it looks like is just a series of dots around the place. And sometimes they form a pattern, sometimes they don't, it really depends on the curve. And he's wondering what if, and there's only a finite amount of these dots, what if the line doesn't actually hit any of them? And the answer is they do, they always do. And the reason, no, the reason they do is because the actual formula here, hang on, I'll just go back a bit. I'm not going to derive the formula, don't worry, but if you do, the way it works is, for example, it's because basically the formulas involved entirely revolve around, multiplying, adding, subtracting integers, and so it's not going to actually get it's not actually ever going to have a fractional answer. Because, for example, I'll just find one line of the thing. For example, once you've got the gradient here, lambda, one of the lines involved, like, 'cause I'm sure you remember, y minus y1 equals m, x minus x1 from, year whatever, you did that. One of the lines involved is saying, I don't know, lambda equals y2 minus y1 over x2 minus x1. And you're probably thinking, well, what if those aren't, what if that doesn't form an integer solution? And the reason is, in this kind of setting, you're doing modular multiplicative maths instead. And so instead, you're doing y2 minus y1 times times x2 minus x1 to the negative 1. Now, you might think, well, that's exactly the same thing. But keep in mind here that it's actually, the symbol here, negative 1, is just a convention depending on whichever group you're doing all these operations in. If you're doing multiplication in the field of real numbers, then you can say that a to the negative 1 equals 1 over a, because by definition that is what the inverse is always going to be. However, if you're doing things in a field of, if you're doing things of integers mod p, let's say you're doing things mod 5. Now, what is 2 to the negative 1 mod 5? Now, you can't just say, it's 1 over 2 because these are all integers. And the answer is 2 to the negative 1 is equal to 3. That might sound strange, but that's because 2 times 3 equals 6. And then 6 mod 5 equals 1. And so this value here isn't 1 over x2 minus x1. It is just whatever number times that equals 1. And in this situation, there will always be integer solutions that form that. And as such, you can always guarantee that in this situation, you always will have a solution that intersects a point on the matrix. Yep. Any other questions? All right, I'll move on then. Is anyone asking anything in the Zoom? Right, just because yell out to me, I can't actually see the Zoom from up here. Yeah, I'll switch back to this now. Great. Good question though. I was going to bring that up, but I didn't want to bore anyone. Yeah. And so quick reminder here, what we're doing is we're solving this quick challenge. Has anyone actually solved this yet? No, Scott. Would have thought someone would have solved it. No. So basically what this is asking us to do is just find a solution, addition of this. So in this case, if you've got So you just define, so once you've defined the subgroup in the curve, you just need to do that first. So you say, subgroup n equals 7940, which is just 9740, which is just the prime plus 1 in this case because the cofactor is 1. H equals 1, yeah, that's the cofactor, and then a G. Now in this case, I'm going to say that the generator is 1, 1. Now, any number theorist would probably scream at me if they saw me doing that because that point doesn't actually lie in the field. I'm just using it as a placeholder because I'm not going to be using the generator. I'm just going to be using my own custom defined points. And when I run this, it will give me an error, but I can just ignore that because that doesn't actually matter in this situation. And I'll say curve equals, field equals F, and then A equals the coefficient of X, which is 497. And then B equals 1768. Test field, yep. Now we've got the curve defined. Now what we need to do is we need to actually define the points. Now this is a lot easier in Sage Maths, and I encourage you to all go and install it, but for the time being you can just say P equals a point. And you need to actually import point as well, I just remembered. Point, curve, and the coordinates here as we were given them. And Q equals the same. And then you can say print P plus Q. Because in this case, now if you want to actually understand this, I highly advise you go and derive the formulas for point addition yourself, but if you're sane, then I think you can just use a library that has it implemented for you. And so if you do that, it will give you an error, but you can ignore that and it'll give you this point here. And so the solution is this coordinate here.